Checkpoint 3. A battery of potential V stores charge Q on a combination of two identical capacitors. What are the potential difference across and the charge on either capacitor if the capacitors are arranged in parallel and in series? So in this question, we have to answer for both potential difference as well as the charge. And also they clearly mention you are connecting two identical capacitors in parallel and series. So first of all, we can just draw the diagram for parallel and series. So here I'm going to draw the diagram for parallel, and here I'm going to draw the diagram for series. So I'm going to take two identical capacitors, and these two capacitors are connected in parallel. So here you can see this is the first capacitor, this is the second capacitor. You can see these are all connected in parallel. Clear? Now you can see both are exactly identical. They clearly mention both are identical capacitor. So we have to apply the concept what we studied from the theory. If the capacitor, so you have two capacitors identical, when you connected the capacitors in parallel, what will happen? The potential across the capacitors will be same. So that means the potential here will be the same. But what happened to the charge? The charge will be different. So based on that, the potential value of these two capacitors will be the same. So that means the answer for the potential difference will be V. But what happened to the charge? So for charge I have to apply the rule, because we have two capacitors. So charge in C as well as C. Because why I put C? Both are identical. So I have to write C1 plus C2, which is equal to, sorry, Q1, because the charge is different, right? So Q1 plus Q2, which is equal to Q, and we know C, which is equal to Q over V. So I have to apply this rule based on the charge. Therefore charge Q, which is equal to C multiplied by V. So here I can write C multiplied by V, because this is for the first capacitor. Both are identical. That's the reason I did not give the number here. And likewise for the second capacitor also the same. So we can write CV, which is equal to Q. So CV plus CV, which is nothing but 2CV, which is equal to Q. Therefore CV, which is equal to Q over 2. So the answer for the charge here is half of the charge. So this is the answer for the capacitors connected in parallel. So potential same and the charge will be half. Now we have to come for series connection. I'm going to use the same identical capacitor. So we are going to connect the capacitors in series. So what will happen? This is the first capacitor, this is the second capacitor. And when you connected the capacitors in series, the charge will be same and the potential is different. So here for the series, charge will be the same. So the answer for the charge is Q, and we have to find the answer for the potential difference. So what I have to do, I have to write the rule V1 plus V2, which is equal to V. That means V1 for the first capacitor, V2 for the second capacitor, but both capacitors are identical. So that's the reason I mentioned C here. So now I'm going to apply the value for V from equation C, which is equal to Q over V. Therefore V, which is equal to Q over C. So I have to apply this rule in place of V1 and V2. So we will get Q over C plus Q over C, which is equal to V. So here we have 2 Q over C. So 2 times of Q over C, which is equal to V. Therefore 2 times of, so therefore Q over C, which is equal to V over 2. So this is the answer. What is the potential? If you connected the capacitors in series, the potential will be half. So V over 2. So this is the answer if you connected the capacitors in series. That's it. Thank you.